Welcome to this lecture. This lecture is based on the beginning of spectroscopy, and from beginning we will move towards the Bohr's model for hydrogen atom spectrum. So, the spectral nature of light present in the rainbow as shown in the figure, and rainbow always attract us and motivate us to explore the nature of light. And another very interesting phenomena of which is known as dispersion of light, as seen here. So when some white light is passed through the prism, it's split into its constituent colors, and these colors are also looks like the colors of rainbow if white light is passed through it. So its journey started a long back, but we will start with 1660. So let us have a brief review of the spectroscopy. So around 1660, let us discuss each point one by one. So in 1660, an English physicist and mathematician, Isaac Newton, he started doing experiments with sunlight and prism. And it demonstrated that white light composed of 7 visible colors. White light composed of 7 visible colors. And this work is documented in a book. The title of the book is Optics or a treatise of reflections refractions, inflections, and color of light. And this book is published in London in 1704. And he starts doing experiments in 1660. And he identified the 7 colors and later on it is known as VIBGYOR. Here this represents the 7 colors. So this R represents red, this O orange, this is yellow, and this is green, this is blue, and this is indigo, and this is violet color. And later on found that it was observed that this visible spectrum means the visible spectrum is this one. This is visible to our eyes. This visible spectrum is a very narrow portion of electromagnetic spectrum. and we can only visualize visible spectrum or the visible region of the electromagnetic spectrum, and rest we cannot identify. And another very interesting thing which people found, that the light which passes through the prism, it split into its constituent colors, and later on this light recombine to give the white light again if we place the prism in this manner. So if we place prisms in this manner, then this will give us a white light again. So if it is a white light, say if this represents a white light, it will go in this way and this way. This will go in this way, and this will go in this way, and it will go this way, right? Then if it passes through this prism, then they may recombine to give later on a white light again. It is white light, it is also white light, and say this is a red and this is blue color, corresponding to violet color in this way, right? And so that means this may happen. So this is the recombination prism, and this will act as to disperse the ray of light, right? That's what will happen. So these experiments performed by Newton. So on the basis of that, he made certain conclusions, and we assume that spectroscopy beginning. Then later, 1802, then later in 1802, William Hyde Wollaston he designed a spectrometer. First spectrometer is designed by him, and what he did, he focused sunlight using lens, and observed the spectrum on the screen. And what he observed certain missing sections, later on called as dark lines in the spectrum. So these missing sections in the spectrum of sunlight was initially assumed to be the boundaries of the colors, or the boundaries between the colors. And later on, this hypothesis was corrected by Fraunhofer. So he corrected that they are not missing boundaries, but they are something else. In 1815, and he used the diffraction grating in place of prism. Diffraction grating was used, and if with this diffraction grating, the resolution of the spectral lines will be improved. So it improved the spectral resolution. And these missing lines which were observed in the Wollaston's experiment, they are known as Fraunhofer lines. Then in 1822, John Herschel and David Brewster they independently investigated the spectra of several colored flames and in 1826 William Fox Talbot suggested that the distinctive pattern in the various spectra could be used in chemical analysis. Then later on in 1835, Charles Wheatstone reported that the different metals could be easily distinguished by different bright lines in their emission spectra, because different metals show different emission spectra. Then in 1849, a very interesting result will come out that J.B.L. Foucault experimentally demonstrated that absorption and emission lines appearing at the same wavelength are both due to same material. Then in 1853, Swedish physicist Anders Jones Angstrom presented theory and observations of gas spectra. He also measured the emission spectrum from hydrogen, and this spectrum of hydrogen atom later, which was studied by Angstrom, this was later known as Balmer series, right? And in 1854 and 1855, David Alter published observations on the spectra of metals and gases. He also independently observed the spectra of hydrogen atom, and later known as Balmer series. Next is a very important observation of spectra used for the identification of chemical elements, and this was started in 1860. Robert Bunsen and Gustav Kirchhoff they systematically studied the spectra systematic study of spectra used for identification of chemical elements. They established the linkage between chemical elements and their unique spectral patterns. Then, in 1885, John Balmer discovered that four lines of hydrogen in the hydrogen spectrum could be expressed in terms of integers, and this series of lines is known as Balmer series. And this observation by the Balmer is later followed by Rydberg in 1888, and he derived a empirical formula for wavelength emitted as 1 over lambda vacuum is equal to RH Rydberg constant for hydrogen atom 1 over N1 square 1 over N2 square. Here N2 is greater than N1. And this RH Rydberg constant, its value is 1.0967758, nearly equal to this, into 10 raised to power 7 per meter, or it is 1.0967758.3 per meter, or it is nearly equal to 13.6 electron volt. We will talk about it later, right? So this is the early beginning of spectroscopy, and later Bohr made a very beautiful effort in 1911 to explain the spectrum of hydrogen atom using quantum theory, and he also derived the Rydberg constant. So we will talk about that in the next lecture. So thanks for watching this lecture.